So today, our talk, 2-letter acronyms with tremendous power, ML and AI. And after the keynote that we had yesterday by Mark Jeffries, I'm going to translate machine learning and artificial intelligence and apply that methodology right away. So we also heard yesterday that it is unanimous with all executives that a digital transformation vision is, you need it. It's necessary in any enterprise. However, the how of it remains a little bit uncertain, unclear. Machine learning and artificial intelligence are pillars of that digital transformation, and that's pretty clear. As I visit customers, I talk to some of you guys, I visit plants, I really sense the urge to do something, and it's understandable because, as Bryce said yesterday, it's very exciting, yet a little doubting and then confusing at some moment. So hopefully, at the end of this talk, we're just trying to give you a possible path to have some successful data science projects. But before we actually get there, let me take a step back and talk a little bit about problem solving. And we really think that machine learning and artificial intelligence required a problem-solving approach that is slightly different. Let me explain a little. So since school, we've been, oriented by a more solution approach, right? And at school, we had a problem that was well-defined, and, we were just focusing on finding that specific a solution for that specific problem. Once we found a solution, we move on to the next problem, and so on. With machine learning and artificial intelligence, it is slightly different because you don't really start with a fixed problem or really well-defined problem or a solution for that matter. So you have this infinite loop that's always driven by the same purpose, though. And you'll see through this talk, when we talk about purpose, we talk about a business case. And we'll really focus on the importance of that business case because that will be the constant of it and will drive, the problem solving and the solution finding. So before going further, I'll just pass it on to Ahmad to just go over, some of the key objectives that we would like to cover, and I'll be back a little bit later.
Thank you, Leila. And good morning, everyone. I really can't see your faces, so if I say something weird or strange, just shout. I can't see your facial expressions. Thanks for the introduction, ladies. So I'm gonna continue what Leila said and put a little bit more paint to this problem, and hopefully by the end of this presentation, you've heard some things and pointers that I'm sure you already knew quite a bit about. Most of it is common sense, but I'm going to put a slightly different spin to it so you have a mental framework to approach a data science problem with more confidence, which matters a lot, and know much better, much deeper, what these terminologies mean, and we're going to talk quite a bit, actually, spend quite a bit of our presentation, both in my piece and when Leila comes back, talks about the real use cases, about a very famous framework or popular framework in the industry, which is cross-industry. If you're happen to be not from pulp and paper, sorry, Mariana, in the room, it still applies. It's cross-industry. It's in the name. And then we're going to connect everything to the Pi system, so you're going to clearly and directly see how OSIsoft products can help you in the process. And then Leila is going to cover a couple really interesting use cases from pulp and paper. All right, so let me give you 10 seconds to read this. So we have all been there, I'm sure, and this part of the technology, machine learning, AI, data mining 5 years ago, who knows what comes next, big data, it's a word soup. And so we know that. The joke is about, you set the stage, and we know that there are a lot of confusing terms. We don't want to get trapped into that, what are words or phrases. It's all about the concepts. So this is the only definition I'm going to give you, and throughout the presentation, we're gonna basically dive into the concepts and give it meaning, as opposed to just talking about dry definitions. And it's pretty simple. I just want to refer to data science as this broad collection of techniques and technologies and algorithms coming from software on one side, or computer science, computer engineering, and statistics to eventually get to knowledge and value from data. Pretty simple. All right, and I'm going to quickly jump into this process that I'm going to introduce and use across this presentation. Leila is going to use that too. And it's called CRISP-DM. It doesn't have anything to do with chips. It's just the name is CRISP. And as you see, it's in the name. It's cross-industry. It's a standard process for the data mining comes from legacy, and it was, I guess, coined 10 years ago when data mining was hot. So don't worry about that too much. And we are going to go in a circle, talk about different phases of this structure to give you a better understanding of the different phases of the process. You can apply this to any analytical problem, any data science problem at your organization. You'll hopefully know by the end of this presentation where to start, what to expect next. The other big point that I like to draw your attention to is the number of arrows that go in different directions. And there's another big one going in a circle, another going back from evaluation to business understanding, which means this is far from a linear process. You should expect quite a few back and forths between your different teams. Things won't work in the first or second or third run. Even when everything is done, you typically have to have an eye on your models and once in a while, retrain your models. Business priorities change. It's very common. I'm yet to see one, linear one end-to-end project that's successful and everything is good. So make that an expectation. So let's start. And what you basically saw in the top phase, which we're going to start from, is like many other projects, common sense, start from a business question. It's important to spend a little bit of time on this, even though it's such a common sense. And believe me, I've been there. I'm an engineer by education myself. How many of you have been in a situation where there's a technical engineer who gets so excited in 5 seconds about this super cool algorithm, and when you ask them why, they're like, because it's so cool, right? So it's much easier to, when you see it on a slide, it makes so much sense. But I'm sure you'll see, I've seen it so many times that eventually when you keep digging, it's hard to connect the actual effort or proposal to a real business value. The other important is the second bullet. You want your question to be sharp, and that's different from goodness of the question. There are some good questions that are not sharp enough. For example, reduce the cost of production. That's a business goal, right? You may want to have it a little bit sharper. You want to say, okay, so cost of production where, what are the parameters? And in many cases, the questions are not sharp enough because it takes work. It's not magical that you just start with an idea that comes to you. You have an epiphany in 1 second, and all of a sudden you push your data and everything magically happens. It takes time to sharpen the question. It takes time to even prioritizing. Do we focus on unit A, on our because our wood chips or water? This is more expensive or that one is more expensive. Even prioritizing what project to tackle first and sharpening the question can be a mini project of its own. And then the other big distinction I'd like to draw is between a business goal and an analytical goal. Because your teams, your projects are intrinsically cross-functional, chances are the different people on your team speak different languages. You've heard that, I'm sure, so many times. And in reality, you need somebody, it might be you in the room or somebody on your team that plays that high-level view kind of role that says, okay, understand the business question. Now, hey, data scientist, data engineer, this is what it means to you. You wanna work on the variance or the correlation between such and such, which can mean nothing to your business leader, and vice versa. So you need an analytical goal eventually for your technical team that supports the business goal. All right, I love this quote because I've seen it so many times. So the goals are awesome and things are great and things happen, but communication is also a huge part of it, which sometimes get lost, especially to engineers like myself. We are all about numbers and the beauty and glory of the algorithms, and you feel like, okay, I got 97% accuracy here. Of course, everybody's going to be jumping up and down. Not necessarily. Numbers put seeds in people's brains. Don't get me wrong. But eventually, what gets people moving off their chair, sign off on something, or start deploying, is connecting with them emotionally. So storytelling, just Google storytelling with data. It's a whole field. There are people who teach storytelling with data. That's all about human connection to actually make it move the needle somewhere and encourage people to act. So invest on that. All right, so we basically covered the inception of your project, which is bringing the business leaders and business understanding and data understanding together. And sometimes, actually, it's quite common that in that discussion, you discover that, oops, actually, we don't have the data. We haven't been collecting data to support this question, so let's start that. In some other cases, the data that you think you're going to need is somewhere hidden, but it's an analytical problem or project of its own to extract data from images, for example, into a different form that can support your problem. All right, so we covered the first inception. So before jumping to the next phase, which starts to get more and more technical, let's briefly talk about a statistical model, what we mean by that. It's basically a mathematical description of a physical or real-world thing. It can be a physical process. It can be a financial system. It can be a combination. And there are traditional ways to look at it with first principles. You write differential equations or physical principles, drive your model. The context of this presentation and data science and AI is usually deriving that model from historical observations, from data. So pretty simple. All right, so here's the next phase. How would you approach, after you understand your analytical and business problems, how would you approach building a model? You've been there. Data is imperfect almost all the times, and there's dirtiness of the data. There is inaccuracies in the data. There are pi tags that everybody believes is collecting temperature from this sensor for 5 years, and only after somebody starts doing something with it, they realize that actually it's been collecting pressure, not temperature. We have been there all the time. There's missing data. So preparation of the data is very important. The other important thing is, even after data is cleaned and good, oftentimes your data scientists need data in a certain shape, which might be different from the existing shape. So reshaping your data, and what in data science is called feature engineering. Features are things that you push into a model and spit out of your model. And it might be, for example, the output of this unit on a weekly basis, and it might not be present in your current data set. So that's a feature that you're interested in, but you have to build it or engineer it. And that happens, that process, between your subject matter experts and your data scientists. And PySystem offers actually quite a few great tools for you to do that. And the beauty of that is that those features on the PySystem sit right next to your data, so you don't have to move data. And you'll see if you decide to move a large amount of data somewhere else to do something analytical on it, it's typically an expensive thing. So you want to bring your analytics to your data as much as possible. Bringing in your subject matter expert is very important. So keep them in the loop all the time. If there's one thing I want to leave you with, don't forget your subject matter expert across the board throughout the process here. All right, and which actually points to this next slide. Process data. If you go out and hire a fresh, typical data scientist out of school, they're great. They're smart. They can do Python and everything. Typically, what they learn from the typical programs, it's not about process manufacturing data, which can be significantly different from, let's say, web data, right? Because of some language differences, we call Pi system, the time series data infrastructure, what a typical data scientist calls a time series algorithm or methodology is something quite different, but the phrases are the same. Also, some of the nuances, say, in the online ad business, if you miscalculate the optimal ad to show, yeah, you might lose a little bit of profit, but nobody dies or nobody blows up. But in our kind of framework, it's very important. That's actually one of the reasons that our industries are a little bit behind. They want to make sure that everything is, all the kinks are sorted out before adopting technology. So there are these nuances. There are quite a few nuances that you want to have, again, your subject matter expert present. Some of the organizations actually decide to invest in-house and educate their existing personnel, let them learn data science exactly because of that. So we talked about how Pi system can help you. Specifically, I've listed a number of products or features. Their event frames is a huge thing. You're gonna leverage them in your feature engineering quite a bit. Okay, here's another important aspect that you wanna pay attention to right from the get-go. So there's significant difference between a project whose end goal is controlling something and predicting something. Why is that so important? Because, number one, sometimes people make assumptions that, okay, here's the data, and the goal is to move this thing that we care about. The question is how. You give it to your smart data scientists, they spend weeks, they come back, all the process is followed, and they say, okay, these two things, if you move them according to our model, you're going to move the thing of your interest. And only then you realize that that thing that they're talking about to move, you don't have access to. It's a deep signal inside your control system. There's no way to fine-tune that, right? So it's true, you can measure it, but you don't have control over it. Another important difference is, controlling means, there should be some causal relationship. And in many cases, prediction is all about, I can predict, but that's it. There's no causation or causal relationship. Let me give you an example. So if I ask you if I present to you a human being, and I ask you, I'm going to give you their shoe size, you tell me, you guess if this person can read or write, right? So I leave you with that. You can't buy someone a bigger shoe and expect them to be able to suddenly read and write. So you can. It's a great predictor, but there's no control power there. Actually, you just Google bogus correlations. There's a website for that, and there's a funny one. There's a bunch of funny ones. There's a strong correlation between the number of movies that Nicolas Cage played in every year and the cheese consumption in the US. They're highly correlated. All right, here's another important factor to keep in mind. We engineers, I include myself, typically, when you talk about a prediction or classification, immediately you go into, okay, how accurate? That's the only thing we care about. It's very important, but that's not the only factor that you need to think about. Why? Because there's cost. There are many different ways that you can peel the onion. There are more complex models. There are simpler models. And as a rule of thumb, if a simpler model is good enough, just stick with that. Sometimes it means sacrificing 2 percentage points on your accuracy. If your business leaders are okay with it, just go with it. Because more complex models, first of all, are harder to explain. They become more and more like a black box. And if a regulator shows up and says, this thing broke, this thing blew up, what happened? And it doesn't pass the test to just say, I don't know, it's just a model. The model said so, right? And then typically simpler models are much easier to at least say that, okay, here's the logic, because it's not black box. The other important factor is that it's costly to implement complex models. They take much more time to implement, troubleshoot, to even deploy. And there's this famous Netflix prize contest that was about, I think, 10 years ago. The prize was $1 million. Back then it was huge, still huge, but even that back then was even bigger. The contest was to predict how a user would rate a movie based on some prior ratings by that user. Data set was provided. It was a big marketing event for Netflix. Many smart people participated. There was a winning team, a lot of glory. They won the money and everything. And guess what? The algorithm was never deployed in production by Netflix, even though they beat Netflix's own algorithm by just precision. Why? Because it was an ensemble or like a collection average of more than 100 different models that they built, and they averaged them out. Netflix, when they did the math, the cost of the engineering cost of deploying it was so high, it basically didn't make any sense. The extra accuracy of the model didn't justify the extra cost of the engineering. So this is an important point. Don't just look at the accuracy of the models. Once your model is done and evaluated by your data scientist, you take it back to your business leaders and ask them, hey, this is what we got. Does it still make sense? Basically evaluate it with them. And it's very common sense. The only point that I want to highlight is that don't think that it's a trivial thing that you just show them over a 10-minute presentation and they're going to be fine. If you're lucky, that's the case. But sometimes they might have different ideas. Actually, in many cases, they get new inspirations, and they're like, oh, now that you're showing me this, I have this new idea. Why don't we do that? And it pushes you back to square one, basically, which is a good thing, but you should anticipate that. And then eventually, we briefly talk about deploying your models. Once you have your model, you want your data engineers, your IT people in the loop. Ideally, you want to have them in the loop in the beginning as well. But they kind of disappear once your data scientists are working on the problem. But they're going to be heavily involved here because it matters for cost and servers, obviously. Governance, data governance is very important. You don't want your data scientists to assume that their model is going to have access in real time to certain measurements that, because of governance, they won't. So there are a number of things that your data engineers are very important. And also sometimes if you're especially from a bigger organization, your data scientists might not be the best resources and they're very expensive. So you may want to just focus them on your data science problems and let your data engineers work on deployment. And then eventually, looking at the big picture, the big circle around the whole thing, everything reproduces itself because physical systems change, so you have to retrain your model. You don't want to start everything from scratch, so you need an infrastructure that, like software, right? Everything repeats easily. Also, there's a stat that it's from last year. The lifespan of a data scientist at a job is, the average is 14 months. That's how hot the job market is. You don't want to bring in every 14 months a new data scientist and start everything from scratch. So your process should be repeatable, and there are up and coming tools in the market for that kind of platform. And like I said, this is your mental image, and the cycle repeats. Before I pass it on to Leila for the use case, I'm going to quickly go over this loop very briefly. Connect every piece or every stage to the Pi system. Data obviously comes from Pi Data Archive. The initial phase, when you want to understand your data and give meaning to different measurements to your business leaders. AF is very crucial. The context plays a big role, saves you a lot of time. And in the exploratory phase of your process, which is typically here, and the next phase, the client tools and the developer tools are crucial. The next phase for your data scientists, event frames, like I said, for feature engineering is very important. The integrators are awesome for saving a lot of time, creating views, right where data is, close to the server. Developer technology, if you have developers in-house. In the next phase, again, the integrators, they're hardened and tested tools for your production environment, so leverage them. I've seen both cases where some organizations go product, some organizations have developers in-house, so they decide to develop things in-house with Python or R. That's also quite good. And then once everything is, you do these parts, there are still some higher level questions. For example, you can still be faced with this question: do you buy or do you build in-house? High level questions like that, which might be best answered through some real use cases from your industry, which Leila is going to walk us through.
Thank you, Ahmad. So yeah, there are a lot of questions that you'll have to ask yourself, and beyond all this, I kind of like that one too. You'll have to kind of choose two, either fast and good, good and cheap, or cheap and fast. Having all three together is kind of the keep dreaming little circle in the middle. But before all of these, questions, I want to put the emphasis on the business case. So now that we've been through the model, the CRISP DM model with Ahmad, I want to take you through two examples, through two use cases where they applied, that CRISP DM methodology for data science projects. I'll be using two examples, one from the pulp side and then one from the paper side of things. So the first use case was about understanding the variability in the pulp viscosity. So again, sharpness of the business case, but at the same time, still pretty open to leave some space to define more and more the problem and the solution. So I'm just going to go through the model again, step by step, but using that use case. So the first step is, once you have your use case, let's do the business understanding of it. So in that case, the target asset was a digester. The current situation that they were facing was just, the visibility after the fact. So not enough insight within the digester itself, and it would affect quality downstream way later. So they couldn't really act on it. So they defined some goals to refine that business case, such as reduction of variability of pulp viscosity, and really also just put the emphasis on understanding the process deeper, and perhaps maybe finding some mystical behavior that they weren't even aware of. They also defined some more specific objectives around these goals, such as really building a predictive model using the current plant conditions. And they put the emphasis on wanting to provide tools for the operator so they could adjust the cooking time according on the viscosity they were seeing live, predicted by the model. So once the business case is understood, then we get to the next step, which is the data understanding. So basically, again, subject matter expert from different fields. It is a teamwork, multidisciplinary field, right? And then you ask yourself what actually influenced viscosity. And then the second thing you need to ask yourself is, well, my data sample, what's going to be the good time range? So for example, if you know that viscosity could be affected by seasons, well, you'll need minimum a year of data. So make sure that you have a significant time range so your data sample is a good one. In this particular case, they were analyzing 8,000 cooks, 4 million record with 100 variables plus each, and that accounted to a total of 450 million data points. So that's a lot of data. We talk a lot about big data. So especially when you have 450 million data points, I cannot emphasize enough on the context, right? That's really where the Pi system can come into place and help you. Asset framework, contextualize, event frame, putting those cooks into those events, and then the Pi integrator for business analytics, just allowing you to clean it. So small little diagram here. You'll have your data that lives in the data archive in your historian, then using AF, as I said, adding context, event frames, tracking systematically your cooks, and then using the Pi integrator for business analytics, having it clean, augment, shape, and then transmit that data into whatever third-party application you're using to do that model itself. So it can really save you a lot of time when it comes to the cleaning. So once you've prepared that data and it's ready to be ingested by the model, in this case, they did some in-house solution. The technology that was used, without going too much into detail, was Microsoft and Azure oriented. And you'll have like just this high-level architecture, which, as I said, the process data and the quality data coming from the process was just historized with data archive, adding context and tracking those event frames via asset framework, using PyIntegrator for business analytics to clean that data, and then pushing this to the Azure Data Factory. From there, that would feed the actual model that was being done in Azure Machine Learning. And then from there, predictions were stored in the Data Factory, and then you can use different visualization tools in order to see those predictions. Then we get into the evaluation phase of things. So it is a training model, so you get into the training the model phase. That's where you might add some process variables, might subtract them, depending on how the result that you're seeing from your models. We can also see that the first iteration data sample had 450 million data points, as I mentioned. The second iteration, they cut this by a factor of 4, so a lot less data points to manage, but they were still covering 3 times more cooks. So they really, you can see with that data sample how they refined their model. And then they were able to move to a live streaming to the cloud. Then quickly over the deployment phase, I'll just kind of say that they realized that 5 minutes was good enough for the predictions that they were looking for. They target just the last cooking phase using 3 different models. And I'll just go to the bottom real quick by saying that they did see some results where they could predict viscosity with a certain level of accuracy. But more interestingly, they did find 2 areas in investigation that they weren't necessarily aware of before that data science project. And one around maybe the whip chip and saying that adding some model upstream and be able to model chip densities or chip moisture, for instance, could better the viscosity model down the line. Moving on rather quickly for the sake of time into the second use case around the paper side of things. The use case here was understanding real quality. I'll just go through that same methodology again, but using that example. So first, business understanding. In this case, the target asset was a paper machine. The situation was just this variability and decrease in the real quality in general. So adding some more specification to, again, understand that business case. So about smoothness, variability, understanding, and smoothness, decrease, and control. So going back to Ahmad's point, are you trying to predict or are you trying to control using your model? In this case, they wanted to do both, right? First, build a predictive model to make sure that you're running, to predict how you're running, and also build an optimization model that could allow you to then tell you how you should be running and help you control your process a little bit more. Moving to the data understanding, same idea as with the viscosity and the digester, right? So, what will affect smoothness and quality? Second question, what time range are we looking at? In this case, it was 1 year again. And another important thing to understand is the frequency of data, right? Process data can come in real time, but then quality data can be very punctual and come just once the reel is actually over and done. And from all of this understanding, they chose a data sample around just 1 paper product, 600 reels, 250 process variables, and 5 quality variables. In terms of the preparation, very similar again to the previous example where Asset Framework can help you give a lot of context to all of that data. And event frames can actually help you track. Because again, a reel can be an event. It has a start and an end. So it can automatically be tracked using event frames. And the other thing great that event frames does is that it kind of reconciled this whole idea of real-time versus punctual data. So I highly love event frames. Then they got into the modeling and evaluation part of things. In this case, they actually outsourced and used an integrator to help them with it. This is the type of modeling that they use, but I won't necessarily go into the details of that. As I mentioned, they wanted to do two things, predict and control. So they used correlative variables to predict. So again, training the model to really kind of narrow it down to what really is a correlative variable and that affects actually smoothness. And then they differentiate those correlative variables with causal variables. These ones are the ones that, as Ahmad said, you can actually manipulate. So they allow you to eventually control your process and optimize it. In terms of testing and evaluation, they did what's called bump test to evaluate both models. So first, to evaluate the predictive model, you'll just do a drastic change in the process, and then you'll just see if your predictive model can actually follow that. And then if that it works, then great. Your predictive model is pretty accurate. And then they did another bump test to see if the optimized model could bring back up the quality to what it was. That's the control part of things. And then in terms of deployment key findings, they did apply it to one paper machine in particular. The prediction model and optimized model became part of an open loop, but we can think that down the line it could be part of a closed loop. And they did give some actionable tools to the operator to be able to, or have recommendation of what they should be doing or what they could do to bring back the smoothness to whatever they want it to be. And then some, results. Quality did get back to the original target. They were able to, maintain that smoothness and other quality metrics. And one other important part as well is the fact that, having that subject matter expert knowledge within these models actually just avoid having, expert moving around and having to go to different mills whenever there's actually a problem in terms of quality. You can leverage these models, and they can act a little bit, to a certain extent, as subject matter experts. So I'm just going to quickly wrap up here. I've been doing a lot of reading about what customers in your industry are doing around machine learning, artificial intelligence, data science projects, and it seems to be a constant. There's kind of 6 key takeaways that seems to be a winning combination or necessary ingredient to these projects. The first one would be that there's this winning combination between in-depth knowledge of the process, in-depth knowledge of the data, and experience. And having these 3, this is really where the money is going to be. The other one is maybe look outside the box. Yes, traditional knowledge is key, but it's vital, but it's not enough. Pat, yesterday, our founder, was saying, augment the scope. That's basically what it means here. Having said that, though, there's a fine line because more is not necessarily better. Bringing only the key variables can actually, from the start, can actually narrow down a lot the variability of your model. So you might save a lot of time right there. You start with, a learning model that will go through some iteration. Once you bring that learning model into a production model, do expect some turbulence there. And then as for the first example I give you around the digester, adding some upstream modeling could be very good and optimize or refine your downstream model, such as adding a model around chip moisture could probably help the modeling of the viscosity down the line. And then finally, I will promote following a certain methodology. It just gives you a good frame for work. So we are a little bit over time, so I'm not sure how much questions we can take. Having said that, I will just touch on a couple of points. We do have a data science pod downstairs that Ahmad's team is there. Myself and Ahmad will be around here during the breaks to answer some questions if you have any. And I want to also redirect you to some labs to echo what Mariana said. There are some data science, machine learning, artificial intelligence oriented labs that are happening on Thursday and on Friday. If ever again you have questions or would like some recommendation, I'll be glad to help out.
Yeah, the pod is at Hilton, not here, not downstairs.
Oh, sorry. Yeah, sorry. The pods are at the Hilton. Yes. And this is us. Thank you.